Hello, I'm Yong Kiam. I'm going to be telling you about joint work with Stefan and Andre done at Carnegie Mellon. And this work is about the study of switch system stability questions from a formal methods perspective. So we're interested in the study of hybrid systems because they allow us to understand the combination of discrete and continuous dynamics present in many real-world systems. For this work, we're interested specifically in the study of stability questions for hybrid systems. So to motivate stability a little, I want you to think about being in a car that's driven by a cruise controller. If you plot the velocity time graph of your car, you probably think of a plot that looks something on the left here, where if your initial velocity of the car is somewhere close to the cruising velocity, then the cruise controller should drive the car near the cruising velocity and eventually get closer and closer to the cruising velocity. However, if you look at the other two plots on this slide, in the middle here, well, the controller drives the car near the cruising velocity, but it kind of oscillates around the cruising velocity and never quite converges to it. While the plot on the right, it does eventually get to the cruising velocity, but it transiently drives the car all the way down to a stop before speeding back up again. Neither of these two controllers would be something that we think of as a correct cruise controller, and the point is that stability is actually a key correctness criteria when we're designing control systems, and if these systems are to be deployed in these safety and mission critical settings, then they also deserve formal proofs of stability. In prior work, we looked at stability verification for differential equations, and in this work, we're interested in stability questions for hybrid or switch systems. So here's an example motivating why we want to use hybrid control. Suppose we have a cut where the controller can either choose to apply an acceleration, or it can choose to apply the brakes to slow the cut down. Now the control objective is to swing up this pendulum into its inverted position, and it turns out that doing this cannot be done with a purely continuous control if we want to swing up this pendulum from all possible initial states. In other words, we must apply some kind of discontinuity in the controller, and one simple form of discontinuity is the use of switching control. There are many other kinds of control laws in the literature which are also based on hybrid control. However, the addition of switching or discrete switching brings with it new subtleties with respect to stability. So in this picture, in the top row here, I have two differential equations which are individually stable. So you can see if the system starts near the origin here, they eventually spiral towards the origin and they stay close. However, given a poorly designed switching mechanism, as in the bottom left picture here, you can see the system, even though it starts close to the origin, it kind of spirals further and further from the origin as it switches between the red and blue differential equations. Okay. So the challenge is we want to provide adequate stability justification when we propose a new switching design. And actually in the controls literature, there are many different stability justifications for different sorts of designs. So either state-dependent switching, time-dependent switching, or even automata-based switching. However, now the question is, what if we have a new switching design that, is different from these, or what if we have one that just combines some of these ideas? How do we give a rigorous and trustworthy proof that our new switching designs actually stable? And that's what we provide in this work. We provide a new stability verification framework that combines ideas from controls and verification. Now, here's the big picture of the ideas from controls and verification that we're going to use. From controls, we take various switching mechanisms, which we model using the language of hybrid programs from verification. From controls, we take the stability notion called uniform global pre-asymptotic stability. I will go into more detail about what I mean by this in the next few slides. But given this stability notion, we specify that using the familiar language of differential dynamic logic, or DL for short. And then from controls, we take proof ideas for stability, namely the idea of using common or multiple Lyapunov functions, and we show how to verify those properties for the stability specification using the classical idea of loop invariants from verification. Now, thanks to this formalization, we can now take examples and case studies from controls, and we can formally verify them using the KeYmaera X theorem prover for DL. Okay, so let me give you a little bit more technical background. when I say a switch system, mathematically speaking, I'm thinking about a family of differential equations, x prime equals to fp of x, along with a set of switching signals, sigma. So intuitively, how that works is that a switching signal prescribes the mode of the system on each time interval. So you can see here, for example, it prescribes sigma equals to 1, then 3, and then 2. Accordingly, the switch system follows this switching signal by following the first differential equation until the first switching time. It switches to the third differential equation, and then at the next switching time, it switches to the second differential equation, and so on and so forth. And you can think about this as a mathematical way of describing a system where there is some kind of switching logic that is choosing between different controllers to apply for a given plant on each time interval. Okay. Now, the other ingredient that we need here is the language of hybrid programs from differential dynamic logic. And the central idea of hybrid programs is to combine continuous and discrete dynamics within the same language. Okay, and I'm showing you the full language here, and you can see here what we're allowed to write down is continuous dynamics in the form of ordinary differential equations. We can also write down the usual operators of discrete programs like assignments, tests, sequential composition, non-deterministic choice, as well as loops. Okay. Now, once we have a hybrid program model, then we can also write down properties that we expect to be true about that model using DL's formula language. So here's the kinds of specifications that we can have. For example, comparisons between two terms. We can express whether a certain property phi and a certain property psi are both true, and so on. We can use the quantifiers. So, for example, is it the case that for all values of a variable x, a certain formula phi is true, or for some values of the variable x, the property phi is true? And most importantly, for our setting, dynamic logic actually provides us with the box and diamond modalities, where the box modality says that for all runs of this hybrid program model, alpha, the post-condition phi is true, and the diamond modality says that for some run of this hybrid program alpha, the post-condition phi is true. And on this slide, the parts that I've highlighted in red, they're actually going to be crucial for us in our stability specification. So, in a previous work published at ADHS last year, we actually show how switch systems can be modeled as hybrid programs, in the sense that these two models actually capture the same set of reachable states. So, in particular, here's an example called arbitrary switching. And the idea of arbitrary switching is that, well, our real-world system exhibits some kind of switching behavior. However, this switching behavior might be too complicated to model. It might not be fully under our control. It might even be controlled by some kind of adversary. Okay, so the idea is we want to have a safe envelope of switching signals. We want our system to exhibit any arbitrary switching behavior. Okay, and the way we can model this switch system as a hybrid program is as follows. We're going to have a big switching loop modeled by the loop operator of DL. And in each loop iteration, what the program does, it starts by essentially choosing which mode non-deterministically to run. And once given that mode, then we just follow the corresponding differential equation for some non-deterministic duration before repeating the loop again. Okay, and this same idea can be used to model more complicated or more complex forms of switching, such as when, as I've mentioned before, when the switching logic is, for example, controlled by some kind of embedded code. Okay, and intuitively, we have the same pattern where we have a big switching loop, and on each loop iteration, we start by applying the controller to pick a mode U, and then we run the mode U for some duration. And the point of these two models actually is to say that, well, switching is modeled by these loops in DL, and accordingly, if we want to specify properties about switch systems, we can specify properties about these switching loops in DL. Now, the specification that we're going to be interested in for this work is stability, and specifically uniform global pre-asymptotic stability. Okay. Now, for this talk, I'm going to just focus in on the uniform stability part of this specification, and just intuitively speaking, stability means that if the system starts close to the origin and it stays close to the origin. And in the context of switch systems, what's important is that if the system starts close to the origin, then it stays close to the origin no matter which switching signal it follows. Okay, so to express this mathematical definition formally, in DL, we essentially represent the quantifiers using the usual connectives of DL. So, for example, what it says is, for all epsilon balls around the origin, there is a smaller delta ball around the origin such that if the system starts within this delta ball, then for all runs of the hybrid program alpha, which models a switch system, in particular for all switching signals modeled by this program alpha, the system always stays within the epsilon ball. Okay, so now that we have our switch system model, as well as our stability specification for the switch system, we can also look at how to actually prove these stability specifications. And of course, the first thing to do is to look at existing ways of proving stability from the literature. And if you're familiar with stability for differential equations, the stability justification for switch systems actually follows from a generalization of the idea of Lyapunov function. And the basic idea is that instead of having the Lyapunov function conditions hold for just one differential equation, we want them to hold for all possible modes of the system. Okay? But we can take another perspective on these stability arguments using ideas from verification. In particular, because arbitrary switching is modeled by these loops, we can use the idea of a loop invariant to understand this Lyapunov function argument. So the idea of a loop invariant is as follows. Now, if the system is initially within this delta ball, what we want to do is we choose an invariant here in blue, right, which is the sub-level set of the Lyapunov function v, characterized by the formula v less than w for some w. Okay, and the idea is that this blue part is going to be preserved across all loop iterations. And what I mean is that, well, initially the system is within this blue sub-level set, and by running one loop iteration of the loop body here, right, so picking a mode and then running that mode for some duration, I should be guaranteed to stay within that invariant. Okay, and briefly speaking, the way this is guaranteed is by ensuring that the derivative of this Lyapunov function is non-positive for all possible choices. Okay, now this means that by running one switching loop iteration, starting from the invariant, we stay in the invariant. Now we can repeat this argument and run one more loop iteration, and we're still going to be in the invariant, and so on and so forth. And what that means is no matter how many iterations of this switching loop that we run, we are always going to stay within the loop invariant inv. Okay. Now this loop invariant is crucial for the formal syntactic proofs, which we develop in the paper. And what you can see at a high level here is that, well, we start with a stability question for our arbitrarily switched system. Okay, what the loop invariant allows us to do is to tie together logic and arithmetic reasoning that we need for this system, as well as the hybrid program reasoning for the different operators that we see in this program. And it allows us to derive the conditions, the arithmetic conditions on the Lyapunov function that we already know from the controls literature. In particular, this allows us to summarize the stability argument as a proof rule in DL, and also, as we will see next, to implement this in KeYmaera X. However, another key point of this loop invariant idea is that we can now take the same deduction and we can apply it to a new switching design that is not one of the standard ones. It's perhaps one that the user defined, where we have some kind of controlled switching. And thanks to this idea of a loop invariant, we can now start from the stability specification and use the loop invariant to derive correct by construction conditions on the Lyapunov functions, here just highlighted in brief in red. Okay, and in particular, these conditions can be derived automatically, and this is what's behind actually our implementation of switch system stability in KeYmaera X. So what we have developed in KeYmaera X is a new modeling and proof interface. So here's the modeling interface. Users can now write down a switch system model in a prototype graph-based language. And what we do with this is we visualize the model, and also we can automatically generate stability specifications from this prototype language. Now, in addition, once we're given a stability specification for a switch system, we also provide a proof interface where all the user needs to do is to provide candidate Lyapunov functions, or if they do not know such a Lyapunov function, the package can actually also automatically generate them for some switching mechanisms using standard sum of squares techniques. In either case, once the system is given a Lyapunov function, either manually or automatically generated, then it actually automates the stability reasoning that we saw in the previous slide using loop invariants. Okay. In addition, in the paper, we also showed that we can also support semi-automated verification of non-standard switching designs. And in particular, we apply this to 3 case studies in the literature. For example, we have the so-called nonholonomic integrator, where we need to switch between an initial controller and another controller once the system is driven to an applicable region. We have a model of longitudinal flight control, where the controller is kind of mediating between 2 different control objectives. And we also have an example of an automated cruise controller where the switching is orchestrated by a hybrid automaton model. Okay, so to summarize, what we have seen here is this combination of ideas, both classical ideas from controls and classical ideas from verification. We use these ideas in order to develop automated support for modeling and trustworthy stability verification of switching designs using DL and KeYmaera X. Thank you.